Hi everyone, my name is Giovanni Geraci. This video is the first one of a series of lectures for the course Signals and Systems 2 at Universitat Pompeu Fabra in Barcelona. The videos are sequential, thus I recommend watching them in the right order. If you have any questions, feel free to get in touch via email, and you can also check my webpage for more information about me. The first class is about continuous time signals. So signals and systems in general arise in a variety of disciplines. In this class, we will start developing a mathematical framework to represent and to work with signals. Signals can describe many different physical phenomena, and the information is contained in the variation of a certain quantity. For example, a car's speed, the fluctuations in acoustic pressure of a sound, the electromagnetic field for a Wi-Fi signal, and so on. So imagine recording a speech like I'm doing right now. You're using a microphone to sense the variations in the acoustic pressure, and these are converted into an electric signal, which is then stored. So in this class, and in the rest of the course for that matter, we will place emphasis on continuous time signals. In the next class, we will introduce the notion of continuous time systems, which operate on continuous time signals. So signals are represented as a function of a variable. Okay, this variable can be time, for example, in the case of a sound. It can be space in the case of an image. Or it can be anything else. It can be altitude, it can be speed itself, it can be depth, anything. A signal could also be a function of two or more variables actually, but for simplicity we will focus on the case of a single independent variable. So there are two types of signals, we could say: continuous time signals, where the independent variable is continuous, and discrete time signals, where the independent variable is discrete. So the former are defined for a continuum of values, for example, speed versus time, okay? While the latter are only defined for a set of discrete values. For example, if you represent weight versus age of a certain population, age takes only discrete values. So 18, 19, 20, 21, etc., for example, right? Discrete time signals may arise from the sampling of continuous time signals. This is very common because digital signal processors are nowadays used to implement many practical systems. And these digital signal processors handle discrete time versions of continuous time signals. In our examples in the following, the independent variable will be time, but it could actually be anything else without loss of generality. So now let us explore the concept of energy and the concept of power of a signal. These are very relevant for many physical signals and systems. For example, the voltage and the current across a resistor, or the power dissipated by a car through friction, etc. So the energy of a signal, x of t over a finite interval between time t1 and time t2, is given by the integral between t1 and t2 of the square magnitude of such signal x of t. Okay? The total energy is obtained in the same way, but by extending the integration from minus infinity to plus infinity. In this case, we are representing it with a procedure of limit, and we get the total energy E infinity, right? The time average power is obtained basically by dividing the energy by the duration of the interval. So we can obtain it by taking the integral between minus t and t of the square magnitude of x, dividing by 2t, which is the duration of the interval, and then taking the limit for t that goes to infinity. This is the time average power. Notice that the signal x of t could possibly be complex, and that is why we use the magnitude. Okay? So in some cases, some of these integrals that we define may not converge. The result might be actually infinity. And this is why we can classify signals as follows in three classes. There are signals with finite total energy. In that case, they have a zero average power, P infinity, because P infinity is obtained as the limit of E, the total energy, divided by 2t for a growing t. And this limit is always obviously zero. We have signals with finite average power. Look, in this case, it's the opposite. If you have a finite average power, P larger than zero, then as a result, your total energy is going to be infinite. And then there are actually signals with infinite power and infinite energy. For example, take the signal x of t equal t. This signal has infinite power and also infinite energy if you just apply the definitions above. So in practical systems, signals are often manipulated and transformed. For example, to transmit a certain command, a signal has to be transformed. To remove noise from a signal, we do a manipulation or a transformation, etc. So now we will get familiar with the most elementary transformations of a signal. Let us start with a simple time shift. So a time shift could be a delay of a signal or an anticipation of a signal. So imagine to start with the signal x of t. From that, you obtain the signal x of t minus t0. So you're subtracting t0 from the independent variable t. So this t0 could be positive or negative, and that has the effect of delaying your signal or anticipating your signal, respectively. So as you can see in the figure, there's an original signal x of t, and this signal is being anticipated. In the example, t0 is negative. It's on the left of the vertical axis. Okay? Another simple transformation, which you see on the right of this slide, is time scaling. So from x of t, we obtain x of alpha t. So depending on the value of alpha, smaller than 1 or larger than 1 in magnitude, the result is that the signal, the original signal, is stretched or compressed. Okay, so you see the original signal x of t in the figure on the right. Below is a compressed version x of 2t, and further below is a stretched and expanded version x of half t. Okay, notice that these transformations that we're seeing on this slide can actually be combined. So you could actually create x of alpha t plus beta, where alpha t provides the scaling and beta provides a shift, delaying or anticipating the signal. Let's move on and see two more examples. So time reversal of a signal consists in basically mirroring the signal, okay? Inverting the independent variable t. So from x of t, you get x of minus t. A practical example of this is playing an audio backwards, okay? This is reversing time for the audio. And you can see the figure on the left where the original signal x of t ends up being mirrored to become x of minus t. It's interesting also to define even and odd signals. So an even signal is identical to its time reverse counterpart, like the figure on the right on top. Okay, so in that case x of t is equal to x of minus t, right? The signal is identical to the time reverse counterpart. An odd signal, on the other hand, is opposite to its time reverse counterpart. So x of t is equal to minus x of minus t. And that's the example you see on the bottom right. That's a not signal. So important classes of signals that we will encounter frequently throughout this course are periodic signals, exponential signals, complex exponential in general, and sinusoidal signals. So let's see more about those. Periodic continuous time signals arise in many contexts. For example, imagine you have an LC circuit with oscillatory behavior where energy is conserved. Well, several quantities in that circuit exhibit oscillatory behavior, the current and the voltage, for example. Okay, so what is a periodic signal? Well, a signal x of t is periodic with period t if x of t is equal to x of t plus capital T. Okay, then this capital T is the period. So as you can see in the example, in the figure, a periodic signal is a signal that periodically repeats itself. It's pretty simple, right? Notice that if x of t is periodic with period t, then it is also periodic with period mt for any integer m. What it means is that that condition up there is also satisfied for mt, right? So it's also periodic with period 2t, 3t, 4t, etc. However, the smallest t for which this condition holds is what we call the fundamental period, t0. Let us look now at exponential and sinusoidal signals. Let's start from a general case. So let's consider x of t equal to c times e to the power of at. Okay, so t as usual is the independent variable, but in this case c and a are complex numbers. They are complex coefficients. So depending on the nature of c and a, we can actually encounter very different situations. Let's see them one by one. The first one is the case of a real exponential. So when c and a are both real, then we obtain a real exponential. There are two cases. Positive a, which corresponds to a growing exponential, and negative a, which corresponds to a decaying exponential. You see this represented in the figure on the right. The top example is for positive a, it's a growing exponential. And the bottom is for negative a, it's a decaying exponential that slowly, or actually pretty fast, goes to zero. Another case is the one of the periodic complex exponential. So again, take the general expression up there, but now instead of considering real a, consider a purely imaginary a. So for example, a is j omega 0. It's a purely imaginary number. Then you get x of t equal to what? E to j omega 0 t. In this example, c is equal to 1. It doesn't really matter. As long as it's real, right? So you obtain x of t equal e to j omega 0 t. This signal is periodic. Where is the period? Well, if we want to find the period, we can just look at the definition of periodic signals and see when that relationship holds. The relationship is e to j omega 0 t equal to e j omega 0 t plus t0. So what is t0? What is the period such that that condition holds? Well, through a simple manipulation, you find that t0 is 2 pi over magnitude of omega 0. Okay, so that is the period. Omega 0 in this case is the fundamental frequency. Then we have yet another case, which is the case of a sinusoidal signal. This is a special case. It's apparently different than the two above, but we will soon see how these are related. So a sinusoidal signal, which we're all familiar with, could be written as x of t equal a cosine of omega 0 t plus phi. Okay, so here omega 0 is defined as 2 pi f0, And t, the independent variable, is for example in seconds. Phi, which is a phase and its constant, is in radians. Omega 0 is in radians per second. And f0 is in hertz, which is equal to 1 divided by seconds. Okay, so let's see what this relationship is. So the relationship between a complex exponential and a sinusoidal signal is as follows. We know that we can write e to j omega 0 t as cosine of omega 0 t plus j sine of omega 0 t, where omega 0 again is called the fundamental frequency. Okay, so there are further formulas that link these different quantities. So for example, a cosine omega 0 t plus a phase phi can be written as a over 2 e to j phi e to j omega 0 t plus the same with the opposite exponents, a over 2 e minus j phi e minus j omega 0 t. Equivalently, you can write a cosine omega 0 t plus phi as a times the real part of that complex exponential, ej omega 0 t plus phi. For the sine, it's the same thing, but you use the imaginary part. So all of this is to say that a complex exponential, ej omega 0 t, has a real part and an imaginary part, and both of them are sinusoidal. The real part can be written as a cosine and the imaginary part can be written as a sine. So they look like those in the figure. In this case, obviously, the frequency omega 0 will regulate the behavior of the cosine and of the sine. You see two examples with two different frequencies and two different periods. In the case above, you have a frequency omega 1, fundamental frequency omega 1, higher, and a period t1 smaller. Below, you have a fundamental frequency omega 2, which is lower, and the period t2, the fundamental period, is correspondingly larger. We'll see more on this later. One thing to add is that these signals have finite energy in one period, but their total energy is infinite because, of course, they have an infinite number of periods. They extend from minus infinity to plus infinity. The average power is finite. Now let's come to the general case, the general complex exponentials. So now let's assume that both a and c in our formula are complex. We can represent c with a polar representation, so magnitude times e to j phase, theta. We can represent a in the Cartesian way, for example, real part r plus j imaginary part omega 0. Okay, if we do this and we manipulate the expressions, then we get that our original expression c e at at can be written in several ways. Okay, we can isolate the magnitude and the phase and multiply it by a complex exponential like the one above, or we can separate real part and imaginary part like the one below. Notice that depending on the nature of R, we will find ourselves in different cases. Let's see which ones. So if R is 0, then we have a special case where the real and imaginary parts are sinusoidal. They are perfectly sinusoidal. Okay? It's what we saw before. If R is positive, then these sinusoidal components are multiplied by an exponential that grows. This looks like the figure on the top right. So there are oscillations, but they are multiplied by a growing exponential. If R is negative, then these oscillations are multiplied by a decaying exponential, like the figure on the bottom right. Okay, let us now introduce the unit impulse and the unit step. These are the last two types of signals we will see today, but they are basic signals of great importance in the analysis of signals and systems. So let's know more about them. The unit step function, also called Heaviside function, is a function that is 0 for negative times and 1 for positive times. It is usually indicated as u of t. Notice that this function is discontinuous at t equals 0, and it is formally not differentiable. Okay? So what can we do to operate with this function, to operate with its derivative? Well, we will consider an approximation of the step function, which we call u delta of t. So basically, instead of looking at a step that instantly, in no time, goes up from 0 to 1, we create a step that takes some time to go up from 0 to 1. It takes a time delta, to be precise, okay? We call this u delta of t. And you see this at the bottom left, okay? From this signal, you can construct its derivative signal. The derivative is illustrated on the bottom right. The derivative is what we call delta delta of t. So of course, this is its value is 1 over delta between 0 and delta, which is when the step goes up, and it's 0 everywhere else because u is constant outside, okay? So it is basically a pulse with duration delta. And as delta gets smaller, this pulse becomes narrower and narrower, but also higher and higher. And its area is always 1, it's constant. This is really important. So what happens in the limit when this delta becomes really small? So in the limit, this delta delta of t becomes a unit impulse, or the Dirac impulse, which is usually indicated with the Greek letter delta. Okay, you can see an example here. The one on the left is unitary, but you can also have a non-unitary one with a value k. It's the one represented on the right. So the area of this impulse is concentrated at time 0, okay? And the area, which is its integral, is 1 or k in general, right? And we can now formally define the relationship between the step function and the unit impulse. So the unit impulse is the derivative of u of t, okay? And u of t, conversely, is the integral of the impulse. This is interesting, and it can also be seen in pictures. If you look at the bottom figure on the bottom right, you see that the integral of delta between minus infinity and t is 1 if t is positive, because in that case the interval of integration includes the impulse, and the impulse has area 1. So you get an integral that is 1. However, if t is negative, then the area of integration does not include the delta, and therefore the integral is 0. So to recap, the integral is 1 for positive time and 0 for negative time, which is exactly u of t. Let us now look at an important property of the impulse, which is the sampling property. So assume that I want to calculate the product x of t times delta delta of t. So the approximation of that impulse that we previously defined, a narrow pulse of duration delta, times a certain signal x of t, whatever signal you like. So for small delta, notice that our signal x of t will be approximately constant in the interval 0 delta. Look at the picture at the bottom, right? The signal x, yeah, it has some variation, but it's almost constant in that interval, especially if delta is small enough. So we could say that the product of x of t times delta delta could be approximated with x of 0 times delta delta, where x of 0 is the value that x of t takes in time 0. Okay? And then if we take the limit, if we make our delta very, very small, then the left side and the right side of that equation converge respectively to x of t times delta of t and x of 0 times delta of t, right? What does that mean? Well, it means that the product between any signal x of t and an impulse is equal to the same impulse multiplied by the value of that signal in 0. More in general, x of t multiplied by a delta centered in t0 is equal to the same delta centered in t0 times the value of the signal x where the delta is placed, which is at time t0. This is an important property. So the unit impulse that we have introduced should be seen as an idealization, right? So while an ideal impulse does not exist in nature, you can think that all systems have a certain inertia, right? So systems take some time to respond to an input. Therefore, if you have a pulse that is sufficiently short, then the system's response to this pulse is actually not affected by the duration of the pulse. It's just affected by its energy, by the area. Okay? So the unit pulse could be regarded as a pulse that is short enough for any system under consideration. So that's all for this class on continuous time signals. In the next class, we will study continuous time systems, which receive continuous time signals as inputs and produce continuous time signals as output. So see you in the next class.